Okay, hello everyone. My name is Abdurrahman Abdu, Research Assistant Civil Engineer from the National Water Research Center in Egypt. Today I will talk about large-scale morphodynamic impact of groups of piers on lowland rivers. Installation of bridge piers in the bed of lowland river has a local and large-scale impact. The local scale impact is local scouring, which leads to bridge failures. 60% of the bridge failure in the United States since 1950 was due to local scouring, while the largest scale impact including bank erosion, sedimentation and bar formation. This sedimentation and bar formation could hinder navigation and block water intakes, which could lead to economic losses. This leads us to our main research question for this presentation. Does the morphodynamic impact of the bridge piers extend to the whole reach? And what is the largest scale morphodynamic impact of applying different bridge piers configuration, like different span characteristics and different number of piers in the transfer section, also different location along the reach, or all of this on the riverbed topography? First, when we install a bridge pier in the river, when the flow hits the upstream side of the bridge pier, there is a stagnation point occur and downflow that tend to impinge on the bed, creating a scour hole. This scour hole trigger formation of horseshoe vortex, which entrain sediment further downstream, while on the downstream side of the bridge piers, a flow separation occur and wake vortices are forming, which also entrain sediment further downstream. About the large scale impact, Musliman and Kislov, they concluded that scour holes that concentrate the flow and create bars and sedimentation on the upstream side of its location, while Azhar concluded that at morphodynamically unstable river, bridge piers form steady bars upstream and downstream, plus migrating bars are forming further downstream, while in morphodynamically stable river, only steady bars are forming upstream and downstream without any further migrating bars. Protection and lining in the vicinity of the bridge piers couldn't prevent formation of these steady bars. It only retreated further upstream and downstream of the protection. Now we come up to the methodology for our research today. First, we choose a reference river, which is a Nile River reach downstream High Aswan Dam in Egypt. It's a sandy lowland river. Then we use 2DH numerical modeling, which is Delft 3D, and we build up a model. We called it Nile River model. Then we carried out calibration scenario, calibration process, until the model could simulate qualitatively the morphological behavior of the reference river, which consists of alternate bar. Then we mimic this physical and the numerical parameters of the Nile River model, and we mimic it and add it to the numerical flume based on calibration, and then we build up our numerical flume and install the bridge piers configuration and apply different scenarios, and then we come up with results and conclusion. First, that is the reference lowland river. We have that's downstream High Aswan Dam from kilometer 14 to kilometer 22 with a total length of 8 km. We have available data like bathymetry, daily average discharge, water levels, and sediment data, which could help us to carry out this calibration process. Then after this calibration process, we build up our numerical flume. As we mentioned before, the numerical flume is a straight channel 16 km, and we choose it long so that it could capture the large scale impact of the bridge piers. The bridge piers dimension are smaller than the main domain, the main course, which we call course domain. So we use 3 domains and connect them using domain decomposition, so that we could simulate the bridge pier, which is smaller than the main course domain. Then, as we mentioned before, we use the calibrated physical and numerical parameter of the Nile River numerical model, and then we added a groin 1 kilometer after the upstream boundary in order to form the alternate hybrid part, which is the case in the lowland river we have. And we run the simulation until the system reaches a steady state. Then we added the bridge piers, different bridge piers scenario. But we have a problem here, is that the system dynamics is very slow, and it reaches after 150 years, it reaches a steady state after a very long time. And with this model, it takes a lot of time. So what we did is that we established a simpler model, uses only one coarse domain for the whole reach, and we used it to simulate the river until it reaches the steady state. And after it reaches the steady state, we take the bathymetry of this initial model and use it as the initial for our main model, where we will simulate the bridge piers. Here's a small video on how the groin would create the alternate bars in our initial bit simulation. As we can see here, here is the groin, is a scar on the other side, and a forced bar are formed in the vicinity of this groin, and it trigger formation alternate migrating bars. They are migrating and tend to elongate, as we can see, and after a time they become more steady. And now that is the final case, where the system reaches the equilibrium with this alternate hybrid bars, and that's the case where we will use in all of our simulations. Here is the best case scenario we will use. We use the average discharge of Nile River reach, and also the average river width, and all characteristics of the Nile River reach we use, like D50 and the bed slope of the Nile River reach. We carried out 5 scenarios with different span characteristics, with different distance between the bridge piers, which leads to different percentage of bridge span over the river width. We carried out also 8 scenarios with different obstruction ratio and number of piers in the transfer section, which means total piers width over the river width. And we carried out 2 simulation with 2 locations in the reach. One location we call the transitional zone, in the area where between the 2 alternate bars, and in the zone where on one side a bar and on the other side a pole. Then we carry out a numerical analysis. We fixed an area for all scenarios for the sake of comparison. This area we chose it in the 1500 meter upstream and downstream the location of the bridge piers. We use the MATLAB script to calculate the percentage of area of scar and the deposition area, also the maximum scar depth, the maximum deposition height. All simulations were carried out for 40 morphological years until the system reaches the equilibrium state. Here's the first set of scenarios, the span variation scenarios. From the results we can see that increasing the span between the 2 bridge piers reduce the deposition on the downstream side of this bridge piers. That's because increasing the span between the bridge piers increases the discharge and the flow velocity between the bridge piers, which could increase the sediment transport and means less deposition. From the numerical analysis we can see that increasing the span between the bridge piers reduce the maximum deposition height and slightly increase the area of deposition, while the area of scour and the maximum scour depths are more or less the same. We can notice also that the area of deposition is always larger than the area of scour in all of this simulation. The second set of scenarios, different number of the bridge pier starting from the center line of the bridge. We can see here that increasing the number of the bridge piers also in the transverse section increases the deposition at the downstream side of the bridge piers, until a point where excessively increasing the number of the bridge piers decreases the deposition on the downstream side, We justify this by when we increase the number of the bridge pier excessively on the cross section, the flow is distributed more uniformly, and also the sediment transport is distributed more uniformly instead of concentrating the flow on the sides, and it's not concentrated in the center line of the river. And that's also what we can see from the numerical analysis, is that the area of deposition is increasing until a point and they tend to decrease again. Also the maximum deposition height, also the area of scour, all of this. Then the third set of scenarios is the location of piers. We have two locations, one in the transitional zone and one in the bar pool zone. From the results here we can see that the impact of installing bridge piers in the transitional zone between two alternate bar is larger than the impact of installing bridge piers in bar pool zone, and that's because in bar pool zone we install the bridge pier in a flow dominated area generated by the presence of the hybrid bar on the other side of the cross section, while here the bridge piers is installed in a transitional area which is not significantly affected by an existing bar, so the bridge piers could show its effect in a symmetric way by forming this central bar, as we can see here. Here is a cumulative bed level changes for the two scenarios. From these scenarios we can also see that the impact of the bridge piers along the whole reach, as it was deposition in the vicinity of the bridge piers and also along the whole reach. And that's for the two simulations. What we concluded from this is that the bridge piers affect the whole reach as they increase deposition to the hybrid alternate bars of the reach with different intensities. We notice that the near alternate bars of the bridge piers are the most affected. Also the bridge piers, from all simulations we conclude that it helps accumulating sediment more than scouring it, as we can see that the deposition area of deposition is always larger than the area of scour in all scenarios. Also we can conclude that the span between bridge piers and the number of the bridge piers in the transfer section control areas and amplitude of deposition and scour. Piers installed in bar pool zone have less impact on the bed morphology than piers in the transitional zone. So we recommend using larger span and more uniformly distributed bridge piers in the river cross section to reduce dredging investment, as it has less impact on the river bed and as a result less deposition. Also we recommend installing bridge piers if possible in a bar pool zone instead of a transitional zone. For future study, in our study we assumed uniform sediment size, but for future study we recommend using different sediment sizes and also takes the effect of bank erosion. In our studies we use only rectangular bridge piers, but we recommend trying different shapes of bridge piers like circular and diamond shapes, so we can study its effect. Also in our study we assumed a uniform eddy viscosity and diffusivity in the Weierstock equation, but we recommend using the effect of horizontal large eddy simulation subgrid model in improving the large scale simulation. That's all. Thank you.